Right, grade 12s. We have to start a new chapter. Chapter 4 on metals. Now, we did metals in grade 8 for the first time. What are the differences in properties between metals and non-metals? Just shortly. Metals are shiny, malleable, ductile, sonorous, good conductors of heat, of electricity. Okay. Now, we are starting out very simply. The chemical properties of metals depend on the arrangement of electrons in the metal atoms. It's basically got to do with how it is bonded. All right. Remember, chemical properties involve making and breaking of chemical bonds. So chemical properties would be properties the substance has due to the bonding between the particles. Now, the physical properties simply on how the atoms are arranged together in the metal crystal. Now, metallic bond, we've done that in grade 10. Who can remember? Yeah. Crystal lattice implies there's an orderly arrangement of particles. These particles are charged. Yes, we say the arrangement, orderly arrangement of positive atomic rests, and they are positive, so where are the negatives? The outer shell electrons, they become delocalized. What does delocalized mean? They can move from one atom to another. It's as if they don't stick to the atom that it should be with. Okay, so here I just have two examples. Zinc, the positive atomic rest has a charge of +2. So each zinc ion is responsible for giving off 2 electrons that can travel through the metal. Sodium has a charge of +1. There's only one outer shell electron, so each sodium atom is responsible for giving off 1 electron, or allowing 1 electron to be delocalized. Yes, probably. Okay. The properties of metals, we've just done them: shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. And then we go and add, usually, metals have high melting and boiling points. What are the exceptions? Group 1 and 2 metals. And usually they have high densities. What are the exceptions? Group 1 and 2. Okay. So, if we have to explain the physical properties of metals, why are they shiny, why are they malleable, why are they ductile, it all goes back basically to the delocalized electrons and the fact that the positive atomic rests are packed in layers in an orderly arrangement, a repeating pattern. So, why do metals have high boiling points? What forces hold these particles together? Why don't the positive atomic rests jump apart? There are delocalized electrons that hold them together. It is an electrostatic force. Coulomb forces are fairly strong. Yeah. So, atoms are held together by strong Coulomb forces. If those forces are strong, we require a lot of energy to separate the nuclei from each other, or the ions from each other. Why do metals have high densities? Same reason. Forces holding particles together are strong. If you have stronger forces pulling particles in closer, it'll be more dense. So, forces holding the particles together are strong, therefore the particles are arranged close together. Why can they conduct electricity. Now, yes, but why does the outer shell electron become delocalized? We say that metals have low ionization energies. Now, ionization is the energy involved in removing an electron from the outer shell, taking it away to infinity. So if metals have low ionization energies, they don't have a strong attractive force on the outer shell electrons. Do you follow? So, metals have low ionization energies. Therefore, the outer shell electrons are delocalized. It's easy to remove them because the force holding them in the outer shell is not strong. And they can travel through the metal. Electrons will travel away from the negative terminal if you put a potential difference across a metal, and it will travel towards the positive terminal. Why? Yes, opposite attract, like charges repel. Conductivity of metals. Why are metals good conductors? Yes, they have delocalized electrons that can travel through the metal. Now, in terms of heat conductivity, there are two ways in which heat can be, three ways in which heat can be transferred. The one is by conduction. What does the definition, the word conduction mean? Energy, bumps or particles vibrate, they bump into each other and it transfers the energy by direct contact. So, the positive atomic rests, they gain energy, they start vibrating and they can bump into each other, transferring the energy by direct contact. The other thing is that the electrons are delocalized and they can also pick up energy and move more. All right. Delocalized electrons can carry the energy through the metal. Yes. They aren't stuck around in the outer shell. They are removed from the outer shell. Okay, so these delocalized electrons also play a role. They also go bumping into the positive atomic rests, and that also transfers energy. Okay, so both heat conductivity and electrical conductivity, due to the delocalized electrons that can move, the heat conduction is very good in metals because the positive atomic rests can vibrate and transfer the energy by conduction, direct contact, and the electrons can also move and carry the energy. The next property, malleability and ductile, they go together. The collective word for this is they are workable. All right? Meaning you can hit it with a hammer, it won't shatter, but you'll hit a dent into it. It'll change shape. And you can pull metals into threads. We call those threads wires. All right. Now, why can this be done? Well, very simply, these positive atomic rests are arranged in layers, orderly arrangement of particles. And between the positive atomic rests, in terms of layers, there are delocalized electrons. So in its simplest form, if I start pulling on a metal, I can stretch, not really stretch it, but I can make it longer if I pull a piece of metal. The reason why is these positive atomic rests can slide off each other without breaking apart because the delocalized electrons maintain the attractive force between the separate layers. Okay, and within a layer as well. So that is ductile. Why malleable? Just very simply, if you hit it with a hammer, you force positive atomic rests out of their orderly arrangement. But it doesn't matter because there are negative delocalized electrons that still hold them together. Okay, so bonds holding the atoms together in the crystal lattice are strong but not rigid. And they aren't rigid because of the delocalized electrons. The sea of electrons keep the layers together, allows the positive atomic rests to slide off each other. That's the end there. Now, from the work you've done in grade 9 at some other point, we did the reactivity of metals. Grade 10. Some metals are more reactive than others. How could I prove that to you? Yes. Take a block of sodium, put it on the desk, leave it there for a while. What's going to happen? It's going to start burning. Okay? Take a piece of steel, put it outside in the rain. After a while, it's going to rust. Okay. What about gold? When ships sink carrying gold coins, do those gold coins rust away in the oceans? No. Hundreds of years later, they can be dived up from the seabed. They have not reacted with the water or the oxygen or any of the salts present in the water. Why that? They are unreactive. All right, so we can set up a reactivity series. Some metals are definitely more reactive, okay, than others. In terms of being more reactive, what does it mean? It actually means that they have a greater tendency to form ions. How do metals form ions? They lose their outer shell electrons. In other words, it comes down to metals have low ionization energies. But within that concept, some metals have lower ionization energies than others. Those with the lowest would be the most reactive because they easily give off their outer shell electrons. The less reactive ones tend to hold on to their outer shell electrons more than the more reactive ones. So we can set up a reactivity series. You know the group 1 metals are more reactive as we go down the group. Similarly, the group 2 metals also. Now, it can be more complicated than this, but your syllabus simply refers to, I think, a little bit on the reactive range, a little bit on the less reactive range, and a little bit on the least or unreactive range. So, for your purposes, you must know potassium is the most reactive. Okay? Very reactive. Sodium, similarly. Even more, actually, than potassium. Now, no, potassium is? Sodium, potassium. Potassium is more reactive than sodium. Yeah, I've got it there. I thought I had it the other way around. So potassium, very reactive, then sodium. And as we go down the board, I can, for example, store a piece of calcium in a bottle or on the shelf, and it won't necessarily start burning. But after a couple of weeks, a white heap of powder will be left. Calcium oxide would have formed. Yes, it's oxidized. Magnesium is also very reactive. I can take a Bunsen burner and I can hold it in the flame and the magnesium will start burning. Zinc, less reactive than magnesium. Iron, less than zinc. Lead, becoming unreactive. Copper, less. Silver, gold, and platinum. Oh, unreactive. Why do they make jewelry from silver, gold, and platinum? They remain shiny. You with me? No? Yeah. So, these elements are unreactive. They don't want to react. It's not that it's impossible for them to react. How is the gold mined at B2 Gold? In what form? Pure little lumps of gold? No. That they do in Alaska in the cold water? No, not solid gold. It's mined as an ore, which is a compound containing gold. All right. Yeah. So it's not impossible for these metals to react. It's just they don't really like to react. All right. If you look at them, if we heat the metals, the more reactive ones will burn with a flame. Sodium and potassium. Sodium has, if I remember correctly, a yellowish flame, and potassium has a purple flame. This color purple. Yes, if I put them in a flame. Or, well, sometimes potassium and sodium, I can just leave. But, yes, and you heat it up, it's going to go even better. Then the elements, zinc and iron, and then from there, they don't burn. I can heat them up, they won't burn. These cars that started spontaneously burning. You know what I'm talking about? What was the problem? Yes, they reckon, if I've got the story correctly, somewhere in the gearbox they use an alloy containing lots of magnesium because it's light and it's strong. And then, apparently, one of the seals tend to break easily. And it doesn't insulate the gearbox part from the heat. And at a certain point, if you've been driving long enough, there's a lot of heat generated, and if you've got enough heat, it starts burning. And you cannot easily put out a magnesium flame. It burns very violently. And that is why, even if they try pouring water on it or using a fire extinguisher, you usually don't have enough to put out the flame. Magnesium burns with a very bright white flame. Yeah. Okay, that's why they use it in flares. They add magnesium to the flare, makes the very bright white light. Okay. The metals then from zinc down to platinum, gold, copper, silver, those, they do not burn. Okay, but they do eventually react with the air to form an oxide, so the surface will become dull. That is why if you have got copper ornaments at home, so after a long period of time they become dull and you need to polish them up. When you polish them, you remove that oxide layer. So this is usually those metals. The zinc oxide that forms on the layer, zinc oxide has a whitish color. Iron oxide, a reddish brown. Lead oxide, I think, is also white. And copper oxide, blue-green color. All right. If we're going to have a look at the reaction of these metals with steam in comparison to the reaction of metals with cold water, we find that sodium, potassium, calcium, magnesium, zinc, iron react fairly easily with steam. Okay? And the products that are formed are hydrogen and the metal oxide. So, for example, if I took sodium and I made it react with steam, I am going to get sodium oxide, okay, plus hydrogen. Interestingly enough, if I make them react with cold water, I don't get the oxide, I will get the hydroxide. Okay. Lead and copper tend not to react with steam. Sometimes you can encourage copper to react by heating it fairly high. If you have two flames, you can heat up the copper, and if you've got finely divided copper, and you've got some water trapped in a test tube, and you heat it and it starts boiling, and the whole system is hot enough, the water doesn't condense. If the steam then makes contact with a very hot copper, it sometimes tends to form copper oxide plus hydrogen. Reactions of the metals with acids. When a metal reacts with an acid, products are salt and hydrogen. So, sodium, potassium, and calcium, people, they react violently with water. I will not add them to an acid. Those reactions will be very, very violent. The reaction is also exothermic, so the metals tend to melt. They have low melting and boiling points, so they form a liquid. And they react violently with the water, so it can cause them to splutter and splash. And if some of that hot, burning metal lands on you, you can't add water to kill it. All right? Yeah, it will burn a hole in your flesh. So we don't add these metals to acids, but if you would, you will have an extremely violent reaction. Product will also be a salt and hydrogen gas. By the way, how do we test for hydrogen? Burning splint makes a blue flame, popping or whistling sound. Magnesium, zinc, and iron, they react fairly decently with an acid fairly controlled in a container. It will bubble, the container will become hot. It will form the salt plus hydrogen. For example, if I add zinc to hydrochloric acid, what salt will I get? Zinc chloride plus hydrogen gas. All right. If they ask you include state symbols, then you have to do it. Yeah? Magnesium. Yes. Because it's slightly more reactive than the others. Okay. Oh, you can also go and look at the balancing of the equation. If you have zinc chloride, you will need 2 there. So that one will give you, for every 2 molecules of acid, you'll get 1 molecule of hydrogen. If we looked at something like, let's take aluminium. Okay, aluminium messes a person around, but if you could get it to react, if we made it react with HCl, it will require some encouragement, but we will get aluminium chloride plus how many hydrogens? So we would not have 3 there, we would have 6 there. So we would get 3 hydrogen molecules. Okay. No, not too bad. Okay. Let's do one new thing. Yeah. In grade 8, 9, 10, somewhere along the line, you did the concept of galvanizing. Who can remember what galvanizing is? Covering a more reactive metal with a, no, covering a less reactive metal with a more reactive one. Zinc coating or gold plating or whatever. Okay. The galvanized iron sheets on the roof, they've been galvanized. It's iron dipped in zinc. The zinc is more reactive than the iron. Zinc is more reactive than iron. All right? And the zinc prevents the iron from rusting. Why? How does it do that? We find because their reactivities differ, these two metals fight over electrons. The more reactive one tends to give its electrons away. So, what is going to happen is if I have, let's just leave those for a moment. If we go and look at galvanizing, I have got iron sheets covered with zinc metal. These two fight over electrons. The zinc is more reactive, so it will give off its electron. But look what happens. If iron would rust, let's say I drilled a hole through it, and it wants to rust over there, we will get iron oxide, Fe2O3. The moment iron oxide comes into contact with zinc, now the whole metal is covered with it. Do corrugated iron sheets rust there where you drill a hole? No, they don't rust. Why don't they rust? Because the zinc competes with the iron ions. This is iron 3+. They fight with each other. The iron wants to get electrons. The zinc is more reactive than the iron, so we get zinc oxide plus iron. So the iron, even though it would start rusting, there's a chemical reaction that pushes it back, that prevents it from forming the iron oxide, because the moment it starts forming, the zinc displaces the iron and it forms zinc oxide and iron. Another property of the zinc oxide is that it is fairly insoluble in water. Iron oxide is very soluble in water. So if I have a piece of steel that's rusting, if it rains, it washes off that layer, and the next layer of iron is exposed and it can rust. The zinc tends not to be water soluble. It is slightly water soluble, but not as soluble as iron oxide. So the zinc oxide forms a layer on the metal sheet. Some corrugated iron roofs, they aren't shiny anymore. Why aren't they shiny? There's some zinc oxide on it. So it's no longer shiny. Now this displacement reaction is commonly known as the thermit process, there, or we refer to it as sacrificial metal protection. Another good example that they do is out in the Walfish Bay Harbour, the ships are made from which metal? Steel, iron. What happens to steel and iron? Because the ships aren't completely painted. Okay? They rust. So what do? They fix strips of magnesium onto the hull on the outside. Magnesium is more reactive than iron. So the moment I have iron oxide and we have somewhere along the metal part the magnesium in contact with the iron, the electrons can be transferred. They're both conductors. They fight over electrons, and magnesium is more reactive than iron, so we will get the formation of magnesium oxide and iron. So the iron doesn't want to rust. Why can't we use magnesium on motor cars? Because of the heat. It is eventually going to start burning. Why can they use it on ships? There's water on the outside. If it starts burning, so what? It's surrounded by water. Do you understand? Okay, so I'm going to stop at this point. There are 4 equations now, especially for you. See which ones will react and which ones won't. When won't it react? For example, this reaction, copper is less reactive than zinc. So the copper cannot displace the zinc. So there's going to be no reaction. So the first one is done. You can figure out the last 3. Grade 12s. Today we have to start and we have to have a look at how we get metals from their ores. Now, the method that we use to get metals from the ores depends on the reactivity of the metal itself. All right. Now, in general, the less reactive metals are easier to extract than the more. In history, first, an Iron Age. Why? The copper and the zinc is unreactive, so it was very easy to extract it from their ores, and the first extractions were probably accidental when they packed a fire in the ground and they made a fire burning. And after the fire had burnt out, they would pick out lumps of brass and bronze from the into whatever they wanted to make. All right, and then later on, when technology had gone slightly further, they realized, but now we can extract iron element to be able to use. No. Okay, so when we talk about metals, when we talk about mining metals, we talk about an ore, O-R-E, that is dug up from the ground. Now, just very simply, the ore is the rock containing the mineral. Now, the mineral is a compound that contains the metal that we are looking for. All right. So, ore is the ground, with the big bulldozers dig it up, when you explode the rocks and the stuff, all the rubble that they pick up, the ore is in that. Now, together with the ore, this desirable part, there are lots of undesirable stuff, sand and, well, parts of rocks, parts of the stuff in the ground that we don't want. Okay, and that has to be extracted. So, when we go and have a look at the extraction of the ore, the first part is the mining. That's when they dig the rocks up from the ground. The second step is to concentrate the ore. Now, it depends a little bit on the ore, how they concentrate the ore. Sometimes it's a very simple process. They allow the ore to slide down a rubber chute due to static electricity that builds up. The ore containing the metal gets one charge, the other stuff has another charge, and it can separate if it falls through a column in which there are oppositely charged electrical plates. Sometimes it's slightly more complicated, and we'll have a look at that as we go down. Yeah. No, that's to extract, it's similar, but that's to extract pollution. Yes, it's a similar process. Okay. Then, when we extract the metal part from the ore that we've mined to the first lump of metal that is recognizable as a metal, all right? They talk about reduction, and I'll explain this process in a moment. And then the last step is to refine the metal further. Usually, this crude metal contains, among other things, carbon. Sometimes when we mine metals, for example, if we take zinc and lead, they are very often mined together and extracted in one furnace. All right. So they talk about a crude metal. It just implies it's not perfectly pure. I don't know if you've ever seen these lorries that come from Chumip with these large blocks of copper on the back. That is the first rough product, okay, from the smelter, and they talk about blister copper. It's fairly impure. There's still carbon and stuff in it. It has to be purified further. All right. Now, so mining, the term mining refers to the digging up of the ore from the ground. We can have an open pit, a quarry, like they do have at B2 Gold, or we can have underground tunnels, like they have in some of the mines in Johannesburg. Yeah, Rospina, okay. I think the open pit mining in general is becoming more and more popular because there are less dangers to it than the underground tunneling. Yeah. Okay, so they are... yeah, because they have to move masses of soil. Yes, yes. And if they have the tunnels, they can go to the veins where the ore lies. Yes. Yeah, so it sort of, makes the process just slightly more viable, I think. Yes, and I think it's also very expensive to build the tunnels, but it's probably cheaper than having to excavate all the soil. So they will know, they'll have their statistics and they'll work it out. Yeah. Okay. Yeah, that's interesting. Okay. One of the problems with these underground tunnels, they're experiencing this in Johannesburg. Some of these mines have been not mined, they aren't mining them anymore. It's like dead mines, it's empty mines sort of thing. But the tunnels are still there, and eventually the structures that they use to fix these tunnels also rots, and it becomes, well, weaker over time. And sometimes the earth shifts a little bit and it breaks certain weight-bearing columns, etc. And they get so-called sinkholes, all right, where the ground just seems to fall away. And it's usually where one of those tunnels collapse, and then the ground above it can't carry it, and then at one point it just gives in, usually when it starts raining very much. Okay. Yes, yes. It has happened fairly often. It's not a obscure thing that happens. No, it does happen. All right, then. So the first step, we mine. The second step, the ore has to be concentrated, because when the ore is dug up from the ground, it also contains rocks and soil and organic matter and pollution and whatever there is in the soil. Okay. The first, or the method, one of the methods in which we can concentrate the ore, I said to you we can use electrostatic attraction under some conditions, but more often they use a process known as froth flotation. And what they go and do is they go and add the ore into a large, well, like a swimming pool, all right? And the crushed rocks are mixed with a specific type of oil together with water. They talk about flotation reagents. Okay, the water is then agitated, it's mixed, and it's like a washing machine, mixes the stuff around, and it starts foaming. And what happens is the ore particles stay on top. It sticks to the foam by means of electrostatic forces, while the unwanted sand and rock and other stuff tends to sink to the bottom, so they can just remove this top layer of foam to extract the ore in a more purified form from the rocks and stuff that they've dug up from the ground. And then this purified ore goes to a process that we call reduction. Okay, and there are various ways of reducing the metals from the ores, and we'll have a look at that when we look at the specific metals. Okay. Right, grade 12, I want to mark the questions that you had for homework. The first one, calculate the energy of a photon of green light with a frequency of 6 times 10 to the power 14 hertz. E equals H times F, Planck's constant, 6.6 times 10 to the power minus 34, and the frequency is given as 6 times 10 to the power 14 hertz. I think I have a set of answers. The first one, what did you get? 3.96, yes, times 10 to the power minus 19, and the unit must be joule. Any questions there? I think that's just straightforward application of the formula E equals H times F. The energy of a photon is directly proportional to its frequency. Now they say a photon of ultraviolet light carries this amount of energy. Calculate the wavelength. Now we know E equals H, which is a constant, times F. So if we need the wavelength, we first have to figure out the frequency. And then from the frequency, we can go V equals F times lambda. The speed is electromagnetic radiation. It's 3 times 10 to the power 8. We've calculated frequency, so then we can determine wavelength. All right? So, first step, E equals H times F. So, F is equal to E divided by H. The energy is 4.95 times 10 to the power minus 19. H is Planck's constant, given the value of 6.6 times 10 to the power minus 34. 6.6 times 10 to the power minus 34. That gives me a value of, did I also get that? Yes, 7.5 times 10 to the power, not negative, 14 is what the frequency must be, yes. If you take minus 34 above the line, it becomes plus 34, minus 19. Okay? It can't be negative. Say again? No, well, it depends on what you get with the value over here. It's also going to affect the answer. All right? And then, if we go to this equation, that one, we know the speed is 3 times 10 to the power 8. We're looking for lambda. So wavelength is going to equal V divided by frequency. The speed is 3 times 10 to the power 8 meters per second. That's just the speed of any electromagnetic wave in a vacuum. We have worked out the frequency over here. 7.5 times 10 to the power 14. And that will give me a wavelength of 4 times 10 to the power minus 7. 4 times 10 to the power minus 7. And this will be in meters because it's wavelength. Who had that one right? Halfway right? Up till there? Did you get that right? Oh, some very good math. All right. Luan? All right. Any questions there? Laura? Yeah. Well, okay. All right, the next one, question 3. A photon of ultraviolet light has a wavelength of 60 nanometer, 60 times 10 to the power minus 9. Okay? It collides with an electron in an atom and ejects an electron. This is the energy. 5 times 10 to the power minus 19 joules of energy are required to liberate the electron. With what kinetic energy does the electron leave the atom? Well, we had a formula yesterday. Kinetic energy is half m. Well, we don't actually need that. We can just say kinetic energy is equal to the energy of the photon, h times f, minus the work function of the metal. Okay? They say this is the energy needed to liberate the electron, so that would be the work function. All right. We have got h times f at 6.6 times 10 to the power minus 34 times the frequency. No, that's the wavelength. Oh, goodness me. All right. What have I done? Can we get to, do we have frequency? But you can work it out similarly. Ne? Speed of a wave, f times lambda. So we're looking for frequency. That is 3 times 10 to the power 8. So frequency is equal to speed of light divided by wavelength. So it's 3 times 10 to the power 8 divided by, now the wavelength is that one, 60 times 10 to the power minus 9. This will give you a value of 5 times 10 to the power 15. 5 times 10 to the power 15, and this would be hertz. All right, now we have a frequency which we can go and put into this equation. I just want to move it up a little bit. So now we can say, I wonder if this whole thing will move. Well, almost the whole thing moving. H times F, there we go. Okay, so now the kinetic energy is going to be H times F, so it is 6.6 times 10 to the power 34. Is it minus 34? Yes. Times the frequency that we've determined there, 5 times 10 to the power 15. Oh, goodness me. 15 minus that one, 5 times 10 to the power minus 19. All right, this is together over there. It gives me 3.3 times 10 to the power minus 18 minus 5 times 10 to the power minus 19. And that will give me a value of 2.8 times 10 to the power minus 18 joules. Okay, who had that one correct? Mooi, well done, Louis. Yeah. All right. All right, the next one. Calculate the period of an electromagnetic radiation of which each photon has a wavelength of that. All right, how much energy does each photon carry? So first of all, we need to get the period. Now, we should know period is equal to 1 over frequency. That's one of the things you're going to use. So we will start off with speed is equal to F times lambda. Yeah? Yeah, speed of light. So we are looking for period, so we actually should get frequency. So frequency is equal to speed of light divided by wavelength. So it's, yeah. Say again. Yeah, it's wavelength. Okay. So we will have 7.5 times 10 to the power minus 7. And this should give you an answer of 4 times 10 to the power 14. 4 times 10 to the power 14 at, all right? Now we've got frequency. They want to know what is the period. So now you say period equals 1 over frequency. So 1 over 4 times 10 to the power of 14, not minus, 14 will equal, the answer is 2.5 times 10 to the power minus 15 seconds. All right, that's the period. And now they say the next part, how much energy does each photon carry? Well, that is fairly easy. E equals H times F. Have we got the frequency? Yes. There. So we have 6.6 times 10 to the power minus 34. That's Planck's constant. Times 4 times 10 to the power 14. And that should give you an answer of 2.64. 2.64 times 10 to the power minus 19, and the unit is the joule. Any questions there? All right. Yes. Just remember, with these questions, we have E equals H times F. But don't forget that the speed of light is equal to V equals F times lambda, and that one is a constant value of 3 times 10 to the power 8 meters per second. You've always got that constant value. That's the one catch, and the second catch then is that period and frequency are mathematical inverse verses of each other. You tend to forget that. Okay, I think we will stop there.
This Omba Arts Trust is not just an organization for me. I think of it in the form of a person, a mother and a friend I have walked and grew with. A friend whom I've traveled many remote and dusty roads. A sister who provided so much needed support during times of fear and uncertainty. There is a saying in Damara for people such as Omba, which is which simply means someone who will, with love, exchange your lean piece of meat with their fat one. It might sound simple when translated, but when used towards a loved and appreciated person, it gives such honor. It describes a person who will do everything to make sure you are taken care of. Besides, we all know how the Damaras love their meat.
Ja, dit sê Maria. Goed. Jy moet 'n bietjie meer reg wees, né? Soos die boere hulle mielies plant. Ja.
I have seen Omba grow and turn into a light of hope for Namibians all over Namibia. I have seen women and men grow as individuals, becoming respected members of their communities, but also valuable providers of their families. I have seen people with no hope in their eyes light up when they see Omba arrive to fulfill a promise which was made and which they did not believe will be kept. I have seen women dance and sing for hours until the dust from their feet covers us all because the old friend has arrived. I've seen women standing up in front of a large number of people and express their hopes and dreams. I've seen people who have never left their village travel hours and hours to other countries and share their culture and experiences. I have seen children grow and become young women and men before my very eyes. Omba has been the sister holding hands throughout it all. Omba has built valuable and strong relationship with communities, empowering both women and men, but the impact on women can be seen and felt most sincerely. The work with the women has such a ripple effect all over the whole village, most especially the young. Omba has taught them to fish. As times grow tougher and much more difficult, money becomes scarce. Environment around us changes and nothing will ever be the same again. In times like this is when we realize the value of a friend like Omba. It provides hope, constant support, reliable income, and keeping us all together, keeping our pots filled and our fires burning. A motivation to do better, live better, and expect better. If one day the unthinkable happens and Omba is no more, it will be a sad time for our Namibian rural population. Therefore, let's keep the light burning at all cost.
Ons die Sanmense is die eerste mense in die wêreld wat vandag agter gaan staan. Omba is nou die water wat vir ons nat maak, dat ons wortels mooi groei, dat ons vrugte kan bring, kos kan bring. Omba gee vir ons werk en van daar af lewe ons.
It's just an amazing story that ostrich eggshell beads, 72,000 years ago, the ancestors of the San were making ostrich eggshell beads, and today in the 2020s, Junko women are still making those beads pretty much in the same way. And the work has evolved from fairly traditional products, this probably would have been worn like this, into something as sophisticated and contemporary as this necklace from the waterfall range. So here we are bringing the necklace to this gallery in Windhoek, and it then gets sold to customers in Europe, in America, and generating income for women, Junko women back in the Kalahari. So it's just an amazing thread of history that goes to this ostrich egg, to this contemporary jewellery. This basket I absolutely love. It's a finely woven basket in natural dyes. This asymmetry is very unique to Namibian baskets, and we've been working with these women, doing workshops and helping them evolve into these incredibly fine baskets. We've worked with the women developing different palettes, and there's another one with a slightly more yellow palette, but considered are the best baskets in Africa. What we're showing you in this short video is really a long journey of working together with rural communities, reviving ancient traditions, turning them into contemporary world-class products, and supporting the livelihoods of over 400 artisans. Even during COVID-19, we've been helping our sand communities with food and a distribution of tippy taps. What we need to do now is to honour the trust that has been put in us over the last 30 years, to support marginalised sand communities and the livelihoods of rural women around Namibia. Your donation will help us get our 400 artisans back to work as soon as possible so that they can feed their families. The lives of their 2,000 family members will directly benefit from this. Please help us raise $50,000 by contributing to the Omba Artisan C19 Support Fund. No matter how big or small, this will make a difference in the lives of our artisans during COVID-19. Thank you.